We're ready to go.
Yeah, thanks, Brian. So, hello everyone. Let me first thank myself for all you for joining me into this webinar. I appreciate your time and hope at the end of this webinar you'll have something to take back and also some learning, if possible. Let me introduce myself. So, I am Srinidhi. I lead DSP team here at AllGo. And we specialize in developing some audio video codecs and also some of the audio post-processing and video post-processing algorithms. So before we get into the presentation, so we would like to mention that we have been working on Hexagon DSP from past 2 years, and so we have been associated with some of the audio codecs optimization development on the Hexagon DSP, and also we have developed some good expertise in developing various algorithms on QDSP. So we thought that it would be good to give some webinar on this topic where we have expertise on the QDSP, and also we have some of the expertise in computer vision algorithms where we have developed in-house, and there are a lot of IPs with us. So we also have ported MP3 encoder on Hexagon QDSP, and which has been optimized for good megahertz. So also we have ported and optimized an application called moving object removal on the QDSP, and this is mainly used in photography, and which we discuss in this session. So we also have been working with various customers where we take proprietary algorithms from them and trying to optimize it on QDSP. So all these more details will be in the following slides. So the agenda for this webinar is, so we will go through overview of AllGo system, who we are and what we do. Later we will have a brief description about the vision-based algorithm which is used in this webinar, and also we will explain you some of the ARM Hexagon DSP split, why we do and how we do about it. Then later we will have some presentation on software optimization implementation details, like how we develop the software, how we optimize the solution. Later we will talk about the demo, and we will have a demo video along with it, and finally we will have a question and answer session. So overview of AllGo systems. So AllGo system was founded in 2005 by ex-Motorola employees. So we have headquarters in Bangalore, and we have a subsidiary office in US and Singapore. Also we have sales offices in Taiwan, Japan and Korea. So our business lines are, we work for automotive infotainment IP and services. So we provide basically the multimedia connectivity, middleware products to automotive OEMs and also tier 1 customers. We also provide some services like BSPs, development, basically the drivers and low-level hardware integration, and we also have some HMI development and also integration as part of this business line. And also we have hardware software turnkey solutions where we develop products for consumer and industrial customer, where we develop both hardware as well as software. We design and do the development, we do the certification, and also we support for pilot production. So we take care like both BOM cost optimized hardware solution here, and also like silicon company focused services where we do some of the multimedia codec development as well as some of the middleware development like GStreamer, Android, and some of the Tizen platforms. Also we have another portfolio of product. So we have video analytics, which is basically done for surveillance, and this has been deployed in various parts of the world, and this mainly has been targeted for some surveillance like left package intrusion detection and basically some illegal parking. So those type of solutions we have the products. So on the highlights, so we have multimedia and connectivity solution for automotive head units. So basically, which I just described in previous slide. Then we have a portfolio of audio and video codecs IPs, which have been optimized on various platforms. And these are basically optimized, leveraging the hardware, the best capabilities of the hardware, and trying to get the best optimization levels. And we do have some strong image processing expertise, so which we have developed some of the vision analytics products. This is the product of our expertise on the image processing. So we have been working on some of the video codecs, and we basically have been optimizing on multi-core platforms where we do break up the video codecs into different chunks and try to run it on different cores of a processor. In turn getting the best optimization possible. So we also have some of the audio video signal processing algorithms like 3D, bars, surround, and some of the video post-processing like de-rinking, de-filtering, some of the smoothing of the video. So we do have some of these expertise. And also we have been doing some work on the image subsystem. So where we have been developing some solutions on the camera system where we integrate the camera and we try to do some of the image quality tuning and some sensor driver development and integration. So we have been working from past on 30 product brands and IC vendors. So we have a big basically customer base. We have been successfully helping them and also into their product and getting into the market. So on the Hexagon DSP highlights, we have optimized our MP3 encoder on Hexagon DSP. We also have developed a vision application on Hexagon DSP, which is the main subject for this webinar. Optimization of some of the customer proprietary algorithms on Hexagon DSP. We have been working with some of the customers where they have their own proprietary algorithms and which they have developed on basically on different platforms. We take it into the Hexagon DSP. So what we offer on Hexagon DSP, so this is basically our into 4 different categories. We can categorize our offerings. One is the domain and the industry focus, services, and licensed software. So on domain, as I mentioned, we have good expertise on audio video codecs, and also we have solutions on computer vision, which we can help the customer getting into their own product and making into a successful product. So industry focus, so we have been working on smartphone and tablets market. We have various solutions into this products. Then we have been working on ADAS, so it's basically concentrated on the automotive industry, so and also on surveillance. So on services, what we provide porting and optimization of modules. So on Hexagon DSP, so we also provide integration of Hexagon DSP modules onto middleware or application framework. It could be Android or any other host OS. We can provide services in helping customer to integrate the Hexagon DSP into the OS. And also we work with third-party algorithm and help the customer to port their solution onto Hexagon DSP. We also offer testing and validation services where we help the customer to test and validate some of their products and try to get the fix or get the solutions working. Also on the licensed software, we provide multimedia audio video codecs. So as I mentioned, we have a good portfolio of audio video codecs, so we provide some of the IPs here. And also we have computer vision libraries, which we can provide as an individual libraries, so that the customer can integrate some of these basic building blocks of a computer vision and try to get the solution working. So yeah, this was the brief description of AllGo. Now we will go into the description of this vision-based algorithm, which is used in this webinar. So the application highlights. So the solution is derived from AllGo Vision's video analytic surveillance software. So as I mentioned, we have an IP where we have surveillance software which has been deployed worldwide, and we derived this demo or the product object removal demo from this software. So we use this is basically used for moving object removal in photography. So if you see in photography, you want to remove some of the background moving object when you're taking a photograph. So you want to remove unwanted moving objects or people moving around behind the scene. So you want to remove them. So this solution is catered for that, and this is used in can be used in photography. And what we do here is we trying to use both ARM and Hexagon DSP. So we try to use the current platform 8974, and we try to implement this solution on the platform. So yeah, so this is a very high level block diagram of the webinar, the demo what we have here. So what we do is we capture an input image from a camera. So we do the color conversion, resize, and we do the background subtraction, where we detect the moving object and we detect the stationary object. We classify them as a background image and a foreground image, and we track the moving object so that we know which is the which object has to be removed at which point of time and things. We track them, and finally we remove the moving object by replacing from the background image to the foreground, so that the object gets removed. And finally we display it on the display. So why basically the main objective of this webinar is to explain why we require this split between ARM and Hexagon DSP. Why can't we run everything on ARM, or why can't we run everything on DSP? So why do we require this split, and why do we require this type of architecture? So the main goal of this split is to get three important points. They are basically the performance, the concurrency, and the power consumption. And nowadays, if you see any embedded system requires a very good performance. Basically, you need to run. There are more and more applications coming into a platform, and you should be able to run them at an optimal bandwidth, megahertz bandwidth. So we need to reduce the overall system megahertz bandwidth. So concurrency. So where we need to free some of the ARM bandwidth, so ARM can do some other processing when we are trying to run this algorithm or different algorithms, and so that the ARM is free to do some other jobs. And power consumption is a very important point, where on embedded systems you require lesser power and the battery life has to be longer. So finally, basically we require a power algorithm or the solution which takes very less power. So these three are the main criteria for why we need to think about getting a good performance on any embedded systems. So what we have the solution here, basically the moving object removal. If you can put some of the very high level description of this algorithm, is basically it needs to do a lot of computation. So where you require to pick up each pixel, analyze each pixel, and you need to take a decision whether it's a background or a foreground or a moving object or a stationary object. So there's a huge computation of the code or the program is happening. So we need to think about how to optimize this computation. Secondly, like algorithms involves DSP and trigonometry. Since these algorithms are very complex, they are all digital signal processing, some of the filtering, some of the FFTs, and they use some of the trigonometry equations, so which are very time consuming, and they are all MAC intensive. on the and since this we work on pixel, and each instruction or computation can be grouped together, so we can parallelize some of this computation and try to run them in parallel. So this is basically helps in type of architecture where you have SIMD architecture. And also load and stores can go in parallel. Basically you are trying to load the data. At the same time, you can compute, some of the computation can be done on the previous load. And also you can store when you're trying to do the computation of the previous or the current one, you can do a store at the parallel. So such things are basically helpful in a VLAW architecture. So modules can be split and run in parallel. So what happens is you run on an image buffer or basically on a huge image buffer, where you can split the image into 3 or 4 entities, and you can run them in parallel. Since the computation doesn't depend on the within the image, across the rows of pixels, you don't have to depend the data. So what you can do is you can split the algorithm and try to run on multiple threads. And also finally we have some data classification and control code where you need to take some decision on whether it's background or foreground or moving object or a stationary object. Such decision and also trying to replace some of the pixels can be is also required. So if you see, this is basically the high level the algorithm, what the algorithm does. So keeping in this in mind, so we move ahead and try to see what Hexagon DSP as well as ARM can do. So Hexagon DSP can do some scalar and vector data operations. So it can do VLAW parallel instruction sets, so where you have different execution units, load units and some of the MAC units, which you can run them in parallel. And since it's a DSP, so it has some zero overhead loops. There are 2 zero overhead loops which you can use, so that you don't have to loop back using some instructions, which automatically the DSP will be able to do it. And there's some compound instruction sets where you can have lesser memory program where this basically can do some of the operations together. Different operations can be done in one instruction. And also it supports some of the circular and bit reverse operations. These are very important when you're trying to do some filtering and some of the FFTs and things like that. There's very good instructions, like one of them is the predicate instruction, where you don't have to have an branch instruction when you're trying to do some if-else condition type of instructions you have. So you can do a predicate instruction there. And also it has a round and shift as part of the MAC instruction. So it's very, very important thing in a DSP type of algorithm. You require round and shift going together along with the MAC. So these are the basic capabilities of the Hexagon DSP. And the ARM capabilities, if you see, it's very efficient for control code execution, efficient in basically database management code, like where you have some of the data where you have to analyze the data, pick up the data, and you have put some histograms and things like that. So you require those type of analysis can be done by ARM. Then it is runs at very high CPU speed. Currently it runs at 2 gigahertz actually. So if you correlate the previous slide and this slide, so we can come up with a design how we can split the algorithm, where which one to run on Hexagon DSP and which one to run on ARM. So if you then finally you come up, basically we have come up with this architecture, like where the brown boxes here corresponds to the code which is running on the Hexagon DSP, and the blue boxes runs on ARM DSP. So if you see these 4 the DSP algorithms, which are like concatenation, resize, background subtraction, and detection, are mainly the MAC intensive and DSP type of algorithms. So where we are trying to push it onto the DSP, and the rest of things we try to keep it on the ARM. So this is a basic split of ARM and DSP, why we took this approach. So later what we have is the software optimization implementation details. Basically it talks about how we develop this software. So some of the key features of this software or software runs both on simulator and hardware. So we have tested it on 8974 hardware, MSM 8974. So we have developed this on Hexagon SDK. So the Hexagon DSP image is a dynamic shared object where images are loaded at runtime. So you don't have to compile the DSP image again and again. You just need to compile your own algorithm, and the Hexagon OS will be able to pick up this image and try to run it run at runtime. So also this helps in incremental build of the algorithm. So you don't have to rebuild all the things on the DSP side. So, and main features, the main kernels of the DSP solution runs on Hexagon DSP. Mainly the Mac intensive and DSP type of applications are running on the Hexagon DSP. So also we have implemented the multi-threading programming. Now this is basically the hardware multi-thread which QDSP supports. Currently on 8974 there are 3 hardware threads. We have utilized in most of the algorithms, we have utilized these 3 hardware threads to make the program, split the program into 3 chunks and try to run them in parallel. This itself we should be able to get a 3x performance basically. So also we have done some of the cache optimization. So we will try to briefly describe how things are done in the following slides. Also, we have done some of the assembly coding, and we also introduce some of the intrinsics so that we don't have to code some of the functions and fully hand coding, but you can still do some of the intrinsics. You can use the intrinsics and get good performance improvement. Also, since Hexagon DSP is an VLAW type of architecture where we are trying to use the packets, where each packets can contain 2 loads or store along with 2 max. So basically you can have 4 different type of instructions running in parallel. So we try to utilize this feature and trying to get the best megahertz for our algorithm. So some of the analytics control code, as I mentioned earlier, we run it on ARM. So basically decision making, some of the pixel replacement, such functions, we try to keep it in ARM and try to run it from ARM side. So moving ahead with some of the optimization techniques which we have done. So as I mentioned, we are trying to use VLAW instruction and as well as MD instruction. So we have used some of the 32x16 multipliers, 16x16 multipliers, 8x8 multipliers. So this some of the instructions which are can go in parallel. So for example, you have like for the first one VMP WEH, where you can try to multiply a 32-bit into 16. So where you have 2 registers which are 32 and another register which are 16-bit. So there are 4 16-bit datas and 2 32-bit datas which can be multiplied. And there's a mux feature also as part of this, where you can pick up the higher or lower register and trying to multiply. Along with this instruction also supports some of the inherent left shift which some of the DSP algorithms requires, and also has a round feature which is also an optional. So which is you can do a rounding after you want to add to the multiplied value, and finally do a shift, pick up their uppermost 32-bit and do an addition along with that, along with the multiplication. So it's a very powerful instruction where like a couple of instructions go together and you get you can do 2 max together in one instruction. Similarly, it is a 16-bit 16 to 16. It's also similar type of instruction where you can do 16 into 16 multiplication and try to basically get the VLAW type of instruction set. So, and also it's the 8-bit 8 is also a similar thing, but at a byte level, 1-bit level, so 8-bit level. So where you can multiply and parallelly multiply different data in a register and accumulate, do the accumulation. So I have shown you one example here where we try to use, so where like VMPY WEH, and there's a 2 multiplication and accumulation along with saturation. So this instruction even saturates. If there's an overflow in your multiplication accumulation, it even saturates and accumulates with the accumulator. So R5 and R4 here are the accumulators, and R7 and R6 are the accumulators. And at the same time, you can load two data into two different registers. So all this can be done in one instruction, which can, all this can go in parallel. So it's a typical SIMD example which has been shown here, and VLIW instruction. And moving ahead, so the Hexagon DSP has zero overhead loops. So there are two nested loops. This is very important feature where you can avoid the branch back latencies and cycles which consumes extra cycles it consumes. With this zero overhead loops, you don't the overheads of branch back can be avoided. So it supports two nested loops where you can have one innermost loop and an outermost loop with zero overhead. And that zero overhead means there's no latencies or the branch cycles gets added in when you want to branch back to the loops, starting of the loops basically. So then we have done some cache optimization. So there are two types of instructions which Hexagon DSP provides. One is the DC fetch and L2 fetch, where you can provide, we can prefetch the data both to the L2 cache as well as the data cache. So especially it's a very good instruction when you're trying to do on an image type of buffer. Basically you're trying to do an one row of pixel you're trying to compute. At the same time, you can initiate and transfer to an cache for the next row of pixel, so that when the program comes to the second row of pixel, it's already in the cache. This really helps in very good performance improvement. Some of the conditional operators, as I mentioned earlier, there are 4 predicate registers. Basically, it avoids some of the conditional instruction. This basically we used from some of the code where you need to do some if-else condition. This piece of predicate register helps in quite a bit of megahertz reduction. Also, we have used some of the shuffle instructions. So this is one of the feature of Hexagon DSP where we used to interchange the data so that the MAC can be done in optimal way, so that we don't have to load the data again and again. So we can shuffle the data within the registers and utilize in the next multiplication and accumulation, so that the reload of the data can be avoided. Sorry about it. This. Okay. Yeah. So further on optimization techniques, so we have utilized the hardware multithreading. So as I mentioned earlier, so we have split some of the algorithms into 3 different chunks, and we are trying to run them in parallel. Some of the modules like image conversion, resize, background subtraction, we were able to split into 3 chunks and trying to run them in parallel. So this helps to achieve close to 3 times the performance gain. Some of the functions with Hexagon DSP which we use were basically worker pool submit, where you submit the jobs, and also there's an atomic increment return. This is basically used to know which thread you are executing. So using this, you can know like you're on a thread 0 or thread 1 or thread 2. At the same time, you need to wait for the job done. So we use the DSP worker pool synchronization token job done. So all these 3 different functions were used in order to do hardware multithreading. So moving ahead, so what was the development procedure which we did? So we first we ported on the simulator. So what basically we tried to do was we ported and optimized so that we get the best optimization, like trying to assembly code, use some of the intrinsics, and trying to see if some of the cache related optimization. So some of the like the simulator provides some good analysis on the cache, how the cache performance is. So we try to use the simulator to do some of this first level of development. So later we moved our code, the solution, onto Hexagon SDK, and we try to test our code on 8974 hardware. So what we did was basically we derived the calculator example code which comes with the Hexagon SDK, and which gives the basic skeleton for our algorithm for development. Later what we did was we took the android.bin and hexagon.bin, two different make files, and we modified these make files in order to include our algorithm files. Later we developed the FastRPC calls, so that we can call the ARM is able to call the DSP modules which are running on the Hexagon. So what we did was first we did the failover based testing. So we give an input buffer image, and we got the output image, and we just offline saw if things has been a background subtraction or the moving object remover is working fine or not. Once this is tested, we integrated our solution with an Android app. So how we did the FastRPC development? So what we did was on the Hexagon SDK, there's an interface ideal file which we used, and inside this ideal file we declared our modules, the modules which runs on the Hexagon DSP. So using the SDK, we built the solution, and which in turn provides automatically provides an FastRPC stub as well as a Skell modules. And this FastRPC stub and Skell talks to the FastRPC driver both on the ARM and Hexagon QDSP. So what this Hexagon SDK uses is basically a Quark ideal compiler, and this is used for interface. This is basically an interface definition language. So basically we need to write the interfaces between the ARM and the DSP. The modules which talks between ARM and DSP has to be written in this Quark ideal compiler language. So also what we did was we used RPC alloc basically for the buffers shared between the ARM and the Hexagon DSP. This avoids basically memory copy at the FastRPC driver level. So basically the QDSP requires a contiguous memory in order to operate. So we need to do an RPC alloc where we can't use the normal malloc, the Android or the Linux malloc, since it's in virtual space and it cannot be in contiguous memory. So what we did was we used RPC alloc in order to get a contiguous memory, and we pass these buffers between ARM and Hexagon DSP. Also, we did used a remote file system which comes along with the Hexagon SDK build. It's used for loading and shared objects on the Hexagon DSP. So moving ahead, so we'll talk about some about the demo, what we developed. So basically, if you see, what we have is there's a camera which talks to the Android app. Android apps basically initiate a image capture, and this Android app sends it to analytics engine. So it basically as an engine where it gets the input buffer and calls the analytics module stub. And this analytics module stub talks to the FastRPC driver, and this FastRPC internally talks to the Hexagon DSP, and Hexagon DSP has analytics Skell, and the analytics Skell will finally talk to the analytics software or the algorithm which is running on the Hexagon DSP. And at the same time, the Hexagon DSP or the software running on the Hexagon DSP performs the computation and gives back the data to the analytics scale and FastRPC, and back to analytics module stub, which is running on the ARM side, and the analytics engine, which is also running on the ARM, will takes the process buffer and gives it back to the Android app, and the Android app will try displays the image. So this is the basic flow. So what we do is we start the preview. So the preview of the camera is started by the Android app, and we capture a series of images, and this image is sent to the analytics. The analytics process this image. Some of the modules, as I mentioned, are running on the Hexagon DSP, and some are running on the ARM. And once the operation is completed, so the analytics generates two sets of images. One is basically an image which is where the moving object is present, another image where the moving object is removed. And this Android app will display both the images, and user has an option to view both the images, where by clicking a button he can see both the images where the moving object is there as well as removed. Once this is done, the things goes back to start the preview. So yeah, on the performance thing, so these are some of the gain or the improvement which we found during our development. So like the image processing, I'm giving an example of an image downsampling code which we did. So on the Hexagon DSP versus ARM, so the C code, just the C code porting, we found an improvement of 1.5x, and on the Hexagon DSP code with intrinsics, just putting the intrinsics, not writing any assembly code or anything, we found an improvement of 3x. Then on the Hexagon DSP assembly coding, by doing some of the assembly coding, hand coding, we were able to get an improvement of 8x. So on multithreading, when we introduced the multithreading, like hardware multithreading on the Hexagon DSP side, we found an improvement of 2.2x. And if you see the overall improvement from the first version of what we have, the bare code, to the assembly coded, multi-threaded coded, we found around 12x improvement. So we will now I will try to show you the demo video where basically we start an Android app, we capture series of images, identify the moving object and stationary object, replace the moving object with a background image. So these are the different steps in the demo video which you will be able to see now. So you see the boy is of interest in the photography, and the person is moving behind the scene. Now the moving object is identified. Now the user is trying to click to remove the object. So the moving object is removed, and basically he can toggle the moving object by there are two different images, as I mentioned. He can toggle those two images and see whether the image is removed or not, the moving object is removed or not. So I can run it once more for people to view it again. So the Android app is started. So the moving object is identified after processing. So the user removes the moving object, and he has an option to see both the images here. Yeah, that brings us to the end of this session. So I think we can get started with the question and answer session.
Okay, folks, if you have questions and answers, we'll open it up now.
No one is present. You can't see it.
Yes, the presentation portion of the webinar is now complete. We're just opening it up for questions and answers.
There is a question audio from Tom Brand. How do you measure performance on Hexagon?
Yeah, I think there's one question from Top Brand. How do you measure performance on Hexagon? So, so we have two type of measurements, both on simulator as well as on the hardware. On the simulator, you can use some of the Hexagon cycles measurement, which the Hexagon tool chain provides. So where you can measure the cycles, so which are more cycle accurate measurements can be done on the simulator. At the same time, you have some of the profiling, which you can do the percentage load also on the simulator, where you can run your algorithm and see which algorithms are taking the percentage wise the megahertz or the computation. So it shows, like, for example, some of the modules can take 80%, some modules take 40%, some modules take 10%. By doing this approach, you will come to know where the most of the cycles are consumed. And later, on the hardware, you can measure on the OS side. On the Hexagon DSP has an OS, QRT Quad OS, which is running, which also provides some of the cycles measurement, which you can tap, and using some of the DSP image logger, you can log that in as a message, and you can see on the ADB shell. If not, you can measure on the ARM side, basically by using some of the timer functions with the Linux support, like get time of the day, which you can see how many microseconds is consumed, the time you initiate a fast RPC call, and you get back the back to the ARM the processed data. So using some of the timer function with Linux supports. So there are different ways of measuring the performance. Okay, welcome. This next question: is there any performance degradation if it is using dynamic loading, then direct integration into the DSP? So the dynamic loading happens only once when you when basically when you're starting off the your module on the first module. Later it is already in the RAM. I don't think that should give any additional degradation in the performance. But this the fast RPC call, there's some overhead, because there's a driver in between ARM and DSP. So there's some few overhead goes in the fast RPC call. Yes, there's a question from Dennis. Is the presentation slides available? Yes, the slides will be available along on the partner web page, and also on our AllGo web page also.
I just sent a link. I just sent a link, Dennis. The slides are up there now. The recording will be up there within 5 minutes after we complete this session. Let me know if you do not have access to that location.
Okay, welcome. There's another question. How is data transferred between ARM and DSP? It is a kind of DMA. So it is exactly, if I understood correctly, the fast RPC mechanism, I don't think there's any DMA, because the RAM is shared between ARM and DSP. But I can get back to you on this more details in case. Yeah, you can. I can. The part of the slides, I have my email ID. You can drop me a mail. Probably I can get back. I believe it is. There's no data transfer, and there's no DMA as such, because the RAM is shared.
can't see the last name contact in this thing. Right stage. I'm gonna ask the brand if
Is Brian, the slides not visible now, or how is it?
Yes, they should be up there on that link I sent.
No, now for the people to see the slides, is it not available?
The slides are published now, yes. The video
Okay.
is not. The video is still being recorded.
Okay, there's another question. I think it is to shared memory driver. So, okay, somebody's clarified the answer. Yeah. Okay, there's another question. What hardware do you... Okay, just hold on. Okay, the next question is, what hardware do you use to develop? Yes, we have used two hardwares, one from 8974, another one is 8074. The 8974 it's a tablet based hardware, and that was provided from B Square. Another one, 8074, was from Intensix. So two type of hardwares we use for our development. Okay. So the next question is, what version of Android? Probably it's the latest one, Jelly Bean. It's a Jelly Bean version. Okay, there's another question. Have you done any audio post-processing module integration on Hexagon? If yes, you can give some pointers. As part of the one of our customer, we have done it, and that's a little bit proprietary algorithm which they had, and we were successfully able to port and integrate on the platform also. Probably you can drop me a mail. Probably I can give you more pointers with respect to that. I'm just typing my email ID for somebody who wants to contact me after this session or later point of time. Will AllGo be, and there's another question, will AllGo be at Mobile World Congress? This I need to check actually, probably.
Sorry?
Will AllGo be at Mobile World Congress? The question is.
We have not yet finalized the
Yeah, I think the answer is probably not yet finalized. Hopefully we should be there actually.
AllGo.
Okay, Trinity. It looks like I don't see any more questions coming in. Do you have any closing comments that you want to make before we
Yeah.
end? Mm-hmm.
Okay. Thanks for everyone for taking time and attending this webinar. Hopefully, I think you have some able to get some info and able to get some of the insights how an Hexagon DSP and ARM development can be done with this session. And in case you have some more questions, you can do write to me, which I've shared my email ID. Yeah.
Yeah, and I'll echo Trinity's comments there. We appreciate your time today and joining us with this session. We're planning on doing additional sessions at least once per month, webinar style. So emails will come out in correspondence with the timing of our newsletters announcing that, and they'll also be published on our Hexagon Developer Network website, so that you could join, and you can also get to the archive versions of the sessions. So yeah, once again we appreciate your time today, and look forward to our next session that we can host for all the ecosystem partners. Okay, thank you everybody.
Thanks very much.
Okay,
Thanks.
bye. Okay,
Bye.
bye.